Good morning to all over here. So we are going to see about an resistance temperature detector. So it is a temperature sensor that is based on the principle of metal resistance increasing with temperature. So what metals we are using over here are platinum and nickel. So platinum, which is to be very repeatable, quite sensitive and very expansive. Whereas the case of a nickel, which is not quite as repeatable, it is to be more sensitive and it is to be less expansive. So when you're saying about tan sensitivity, so actually the RTD sensitivity, which can be noted from typical values of linear fractional change in resistance with temperature. For platinum, the value to be around 0.004 degree per Celsius. For a nickel, the typical value to be around 0.005 degree per Celsius. So thus with platinum, for example, a change of only 0.4 watts would be expected for a 100 watt RTD if the temperature is changed by 1 degree Celsius. When you are saying about a response time, it is around 0.5 to 5 seconds or more. The slowness of response is due principally to the slowness of thermal conductivity in bringing the device into thermal equilibrium with its environment. Generally, time constants are specified either for a free air conditions or an oil bath condition. This are its equivalent. Okay. Construction. It's simply a length of wire whose resistance is to be monitored as a function of temperature. The construction is typically such that the wire is wound on a form to achieve small size and to improve thermal conductivity to decrease response time. In many cases, the coil is protected from the environment by a sheath or a protective tube that inevitably increases response time, but it may be necessary in hostile environments. Construction, they are either a metal film deposited on a former or are wire-wound resistors. The devices are then sealed in a glass ceramic composite material. The electrical resistance of pure metal is positive, increasingly linearly with temperatures. These devices are accurate and can be used to measure temperatures. So this is the composition lines in the RTD circuits, and this is the block diagram where we'll be having of an RTD circuit. So when you're calculating dissipation constants, so LT is equivalent to P by PD. So the thing is to be that temperature rise because of self-heating, P to be the power dissipated, where PD stands for power dissipation constant in the RTD. So when you're saying about a range, it depends on the type of wire what we are used. So typically platinum will have a range from -100 to 650 degree. For the nickel, it will have a range around -180 to 300. So when you're saying about an applications, it is used for air conditioning and refrigeration servicing, furniture servicing, food service processing, medical research, and textile productions. The advantage, most stable over time, most accurate, most repeatable, temperature measurement, very resistant to contaminations, corrections of the RTD element. Whereas the case of a disadvantage, it has high cost, slowest response time, low sensitivity, small temperature changes, sensitive to vibrations, decalibrations if used. The next thing there you need to see about an acoustic wave sensors. So they are so named because the reduction mechanism is a mechanical or acoustic wave. As the acoustic wave propagates through or on the surface of the material, any changes to the characteristics of propagation path affect the velocity or the amplitude of the wave. Changes in velocity which can be monitored by measuring the frequency or phase characteristics of the sensor and can then be correlated to the corresponding physical quantity being measured. Virtually all acoustic wave devices and sensors use a piezoelectric material to generate the acoustic wave. So where the piezoelectricity was discovered by Brothers Pierre and Paul Jacques Curie in 1880. So piezoelectricity refers to the production of electrical charges by the imposition of mechanical stress. So this phenomenon is reciprocal. By applying an appropriate electric field to a piezoelectric materials, it creates a mechanical stress. Similarly, it applies an oscillating electric field to create a mechanical wave which propagates to the substrate and it is then converted back to an electric field for measurement. So when you are saying about an piezoelectric substrate which can be used for acoustic wave sensors and device, the most common are quartz, lithium tantalate, and a lesser degree lithium rhodium. Each has a specific advantages and disadvantages, which includes cost, temperature dependence, and then we'll have around a attenuation and propagation velocity. An interesting property of quartz is that it is possible to select the temperature dependence of the material by the cut angle and the wave propagation direction. With proper selection, the first order temperature effect can be minimized. On acoustic wave temperature sensors may be designed by maximizing this